Welcome to AI Podcast. Today we're digging into a fresh EMNLP paper called Collab Overcooked, and it's all about whether large language models can actually work together like good teammates.
Collaborative agents. I love it. Give me the headline first. What's the quick takeaway?
The short version is this. The authors built a benchmark that forces two agents to collaborate in an overcooked-style kitchen, and then they measured not just if the team finishes the dish, but how the teamwork unfolds. The big finding is that models are pretty good at responding when a partner asks for help, but they're much weaker at initiating help on their own. And as tasks get more complex, performance drops fast.
So it's not just can they make soup, it's can they be good kitchen partners. Who's behind the work?
Lead author Haochen's son with colleagues from Beijing University of Posts and Telecommunications, and the corresponding author is Shuwen. There are more co-authors, but those are two key names.
Great. Now set the scene. What problem in the field are they trying to fix?
A lot of multi-agent evaluations let a single agent quietly do everything, so you get a pass that looks collaborative, but really isn't. And many benchmarks use only a final success score. That hides whether the agents communicated well, divided work sensibly, and adapted when things changed. This paper fills that gap by structuring the kitchen so no one can solo the meal and by scoring the process of cooperation.
How do they force teamwork? What's special about their kitchen?
Picture a restaurant cut into two half kitchens. I'm stuck on the prep side with onions and a pot. You're on the other side with the knives and the sink. We can slide items across a shared counter, but I can't reach your tools and you can't reach mine. On top of that, only one of us knows the recipe. That's resource isolation plus asymmetric knowledge. If we don't communicate, nothing gets served.
That sounds like the pass in a real kitchen. So the agents talk in natural language?
Exactly. They can chat, plan, and then take actions in the environment, and the evaluation looks at the action history, not just the final dish.
All right, talk me through the scoring. You said they measure how the teamwork unfolds. How?
They use something like a yardstick for progress called a trajectory efficiency score. Think of it as comparing what the team actually did to a sensible reference plan. From that, they derive three simple ideas. Progress completeness, which is how far along the plan the team got. Initiating capability, which is how well an agent kicks off helpful steps without being asked. And responding capability, which is how well an agent reacts to a partner's request.
I like that. It's like grading a dance. Did you finish the routine? Who led and who followed gracefully?
Perfect analogy.
What did they test model-wise? And keep it light. No laundry list.
They ran a mix of open and closed models under one unified agent setup. Two names worth calling out. Claude Sonnet 4 did the best overall. DeepSeek R1 was strong among open models, but it used far more tokens to get there, roughly 19 times as many as GPT-4 in their setup.
Wow, so stronger but also hungrier. Did size save the day on the hardest tasks?
Not really. Scaling helped on simple levels, but as the kitchen got busy and the plan got long, all models stumbled. The gap between responding and initiating grew, and the success rate fell sharply.
How did humans do in this kitchen?
They ran a small human baseline. People held up better as complexity increased. Not perfect, but more resilient. Humans are pretty good at noticing when a partner is stuck and stepping in.
That makes sense. We're used to reading the room. Did the authors figure out why the models struggle?
They point to attention misalignment. Models tend to latch onto the recipe text and ignore the evolving state and the partner's needs. It's like staring at the menu while the pot boils over. When the authors nudge the agents to pay attention to the right signals, success on previously failed cases jumped significantly, something like 1/3 to 2/3 better.
So the issue isn't just knowledge. It's what the model chooses to look at mid-task.
Right. Attention allocation and timing. Starting the right subtask at the right moment, asking for help early, and handing off items smoothly.
I want a concrete example. What does a failure look like in this setup?
Sure. Imagine I know the recipe and I tell you, wash the plate, I'll chop onions. You wash, but then you keep washing because you're fixated on cleanliness while I'm waiting for a plate handoff. We both do reasonable actions, but the choreography breaks. Initiation is missing. No one says, I'm ready, slide me the plate now.
And a success?
A good run sounds like this. You wash one plate, say ready on pass. I respond, sliding the chopped onion. You plate, then you ask, need another plate or should I chop? I say chop. That's short, timely turns with clear handoffs. The process score loves that.
Let's talk about evaluation design for a moment. Anything that listeners should keep in mind?
Yes. The human baseline is small, so it's more of a reference than a definitive ranking. Closed-source models can change over time, which makes perfect replication tricky. And the agent architecture is intentionally simple to keep things fair across models. That means stronger planning modules might change the picture. There's also a subtle risk that the reference plans, the trajectories, don't cover every clever strategy a model might invent.
Right? If I find a new recipe path, I shouldn't be penalized just because it wasn't in the handbook.
Exactly. The authors try to keep the yardstick broad, but it's a general challenge.
What about cost and practicality? You mentioned token hunger.
The setup involves long prompts and ongoing dialogue, which can be expensive. That's why the token efficiency differences matter. Two teams can tie on quality, while one quietly burns a lot more compute to get there.
So what do we do with all this? If you're building agents that have to work together, what are the next steps?
First, build collaborative memory. Let agents remember teamwork patterns, not just facts. Second, guide attention. If the environment changes, shift focus toward state and partner signals, not just static instructions. Third, test richer scenarios, maybe more than 2 agents and more open-world kitchens. And finally, evaluate not only success but also quality per token and time to success.
I'm thinking about real teams at work. This sounds like the difference between a colleague who waits for tasks and one who anticipates the next move and makes your life easier.
That's the heart of it. Current models are polite followers. We need proactive partners who see a bottleneck coming and act without being told.
Before we wrap, name the contribution in one line.
A benchmark that truly forces teamwork and shines a light on the mechanics of collaboration, revealing that language models prefer reacting to requests over initiating help, and that careful attention guidance can unlock big gains.
Nice. Final takeaway for listeners?
If you're deploying multi-agent systems, don't just measure whether the job gets done. Measure how the partners coordinate. Watch for initiation gaps, guide attention to the right signals, and budget for token costs.
And keep an eye on Collab Overcooked as a testbed you can actually use. Kudos to the authors, especially Haochen Sun and Kaixia Yuan, for pushing the conversation forward.
That's our show. This is AI Podcast. Thanks for listening, and we'll be back with more research you can use.
See you next time.